This example is from MGF 1107, section 14.2, when we're discussing Euler paths and Euler circuits. In this example, you are given a graph, and in that graph, it is requested for you to find an Euler circuit that begins and ends, since it's a circuit, has to begin and end at the same vertex, and they want you to begin and end your Euler circuit at vertex A. Now, the way I can tell the Euler circuit apart from the Hamiltonian or Hamilton circuit in the next section is Euler, although it doesn't sound like it. Euler starts with E, and so does edge. So the Euler circuits deal with traversing or covering or using all the edges in the graph, whereas the Hamilton or Hamiltonian circuit we concentrate more on the vertices in those type of circuits. So in this graph, we are asked to start at vertex A. Vertex A is right here. And our goal is to find, again, an Euler circuit. So that means we start at A, and at the very end we have to end at A. And in between we may visit A as well. And we have to use all the edges because it's Euler. So from A, it is multiple choice, so what you could do, since it's multiple choice, is follow each one of these paths and see which one is a circuit, and that's a perfectly acceptable way to answer the problem. So example, in part A, answer A, well, that can be eliminated right away because that's not even a circuit because it begins at A, but it does not end at A. So B, C, and D could be the right values. Now, one thing you could do is look at the degrees of each vertex and see if we have any that are odd vertices or if they're all even. Now remember, if they are all even degree, then it would have an Euler circuit. So let's start with A. A has degree 1, 2, 3, 4. B has degree 1 and 2. C has degree 1 and 2. D has degree 1, 2, and 3. E has degree 1, 2, and 3, and F has degree 1 and 2. So in this problem, I think we have an issue because you notice there were two vertices that had an odd degree. D and E were two vertices that had degree 3, which is odd. And according to Euler's theorem, it says a graph with exactly two odd vertices has at least one Euler path, but no Euler circuits. So in this case, we have odd vertices, two odd vertices, matter of fact. Thus, it might have an Euler path, but it doesn't have an Euler circuit. According to Euler's theorem, a graph with exactly two odd vertices has at least one Euler path, but no Euler circuit where the beginning vertex and the end vertex is the same.